Okay, so in this video, we're going to be doing the solutions for assignment number 1. Okay, so question 1 asks us for each of the following statements to give both the converse and contrapositive as well. So the first one is if n is even and n is strictly greater than 10, then n squared is even. So first thing, we have to break up this into our component sentences and then write our converse and contrapositive. Okay, so part A asks us, this is question number 1, if n is even. So I'm going to take that first part at the beginning of the sentence where it says if n is even and n is strictly greater than 10. I'm going to let P be the statement that n is even and n is strictly greater than 10. And then I'm going to take the second part and I'm going to say let Q be equal to just n squared is even. Okay, and then for the converse of the statement if P, remember, if we have something like if P then Q, converse is if Q then P, right? So I just have to take the statement and switch them around. So I'll get for the converse part, I will get if n squared is even, then n is even and n is strictly greater than 10. Okay, so this is the converse part. Now the contrapositive part now is if you have a statement of the form if P then Q, the contrapositive is if not Q then not P, right? So now I need to take the statement and flip it around and put a negation on them. So for the second statement, which we have the P part, which is not P, so not P will be not of the statement n is even and n is strictly greater than 10. So I need to bring the negation on the inside. Okay, I need to bring the negation on the inside. So when I bring the negation on the inside, I will get that n is not even. And then when the negation comes into an and statement, this here, then the and statement changes to an or statement. Sorry, connective statement, right? So I'll have or n. So now we have the opposite of what is n is strictly greater than 10, which is n is less than or equal to 10. So let's put this all together now. So for the contrapositive, I have that if n squared is odd, then n is not even, or if you want to use not if you want to use odd, okay, that's fine as well, or n is less than 10. Okay, so this is part A. Now part B, the other statement is if the correct username and password are entered, then access will be granted. Okay, so a similar statement to what is done before in terms of structure, right? So I'll have to separate it once again. So I will let P be equal to the correct username and password are entered, and let q equal to access will be granted. So now I need to find the converse and the contrapositive. So for the converse, I will have if q then p, so converse. If access will be granted, then the correct user name and password are entered. Okay, and for the contrapositive, if now I'll have if not q, then not p. So I'll have if access will not be granted, will not be granted, right? Some people might write here is not granted. Okay, then the correct username, and just like before where the and has changed to an or, we'll also have or the password were not entered. Okay, so this is question 1, A and B. So let's move on to question number 2 now. Question number 2 asks us to write part A formal negation for the following statement. Part B also asks for a formal negation. So they both ask for formal negation. So let's do a negation of both of them. So question number 2, part A. So we have the statement for all x that is real, as x run through the set of real numbers, x is strictly greater than 0, implies that there exists a y that is real, such that y squared is equal to x, close parenthesis. Okay, now I need to negate this statement here. So first thing I want to do is, okay, I want to put a negation sign, right? And I'm going to put a square parenthesis. I'm going to negate the entire statement. So we'll do it in parts. So for all x that is real, I'll put back this x is strictly greater than 0 implies that there exists an y that is real as such that y squared is equal to x. Now let's go step by step. First one here is to put the negation inside this negation here inside here. When I negate a for all, I'll get a existential quantifier there exists. So there exists an x that is real, right? So you're going to do this first part here first. So let's keep it as red. So I'll have there exists x that is real, and then I'm going to put in negation here. So we're doing it in parts. 0 implies that y is real as such that y squared is equal to x. Close. Okay, Now the next step, I want to negate this here, take this negation sign, and I'm going to negate on the inside here. When I negate from the inside here, the implication will change to an and sign, right? And then the negation is going to come in front of this there exists sign, and the there exists sign is going to change to a for all sign. So I'm going to have this and sign here changing. This quantifier here is going to change, and y is going to be real. And then now the negation is going to have to negate this as well. Y squared is equal to x. So if y squared is equal to x is our statement, then the negation of y squared is equal to x is y squared is not equal to x. Okay? So we can do all of that in one step. Let's keep the bracket here. This is greater than 0. Right? So the implication will change to an and. For all y is real, y squared is not equal to x. And we have successfully negated this, right? Of course, if you wanted to take the negation here and then put it inside and then show how you negated all of this, that's fine as well, right? But I'm just doing this to save time. Okay. Let us move on to part B now. So another formal negation that's a little bit different. So part B says, okay, let's write out part B. We have that there exists an n that's an integer for all m that is an integer as well. M is greater than or equal to n. Okay, the structure looks a little bit strange. It could have said as well for all of the first and then there exists of the second, right? But the there exists is first, which is fine as well. So let's negate the entire thing. So let's put our negation sign with our there exists sign. There is an integer for all m that's an integer as well. And I have that m is greater than or equal to n. Close parentheses. So now I'm going to take the negation here and I'm going to bring it on the inside here. I'm going to negate the there exists. So it's going to become a for all. Then I'm going to negate. Okay, so let's do it in parts. Then I'll put a negation here and then I'll put a different parenthesis. The first one is to negate the there exists. So it becomes for all. And that's an integer. Then I'll negate from here. Of course, you can do all of this in one step, right? But we're just doing it in different steps for the purpose of the explanation. Now, the negation is going to come on the inside here. And when this comes on the inside, this for all is going to change to a there exists, right? And then we're also going to have to negate this here. And this negation here, the negation of something that's greater than or equal to something is strictly less than. Okay, so let's write that out. We have for all, and that's an integer. There exists an m that is an integer such that m is strictly less than n. And this is your negation here for this statement. All right, let's move on to part C. So C has two subparts, right? So they ask us here to find the truth values of S1 and S2 and also to give a justification for each one. So The truth value here is just whether to state whether the statement is true or false, right? And but we have to justify why, right? So we have to look at the domain of each statement and then look at what values that satisfy this and then be able to make an assertion based on that. All right, so let's do that. This is C subpart 1. So I'm looking at the two statements here. I'm just going to split the screen for a second. The canvas doesn't allow it, so you'll only see this screen. Okay, there we go. So I'm going to say that S1 is true, and I'm going to say that S2 is false. So let's look first as S1. S1 says, given any real number, there's this y that is real, such that y is equal to x cubed minus x. So S1 is saying given, let's just write this out in words, given any x that is real, then I have to choose some y that is equal to x cubed minus x, which is also real. Is that always true, right? So that is the question. Is that statement always true? Well, if I choose, let's just say the number 2 or something like that, right? 2 cubed will give me 8. 8 minus 2 will give me 6. And 6 is a real number, so this is fine, so right? So this satisfies the statement. So we could say, therefore, S1 is true and the statement holds. Okay. So for part 2 now, I said that it is false, right? It looks false. Part 2 is saying that there exists a y that is real. For all x that is real, y is equal to x cubed minus x for all x. So this is saying that there is a real number, like one single real number y, that will equal to x cubed minus x for every real x. But remember, if I have something like x cubed minus x, which they gave me, right, then my value of x here will change, right? Because if I put something like let's use back the 2 again, right? So if I use back the 2, then this side will give me 8 minus 2, which is 6. But y is equal to 2 here, which is not equal to 6. So no, it doesn't work for any fixed y. So S2 is false. Okay? We could even say this is impossible. So no such y exist. Okay, and any counterexample will work. So right, so you could choose any value you wish and you could show that it does not hold. Let's move on now to question 3. So it says, determine which of the following equivalences are valid or not. All right, so some of them may not be valid by simplifying one of the statements, right? So we can choose either the left hand side or the right hand side. Justify each step by giving the name of any logical equivalence used, right? So any equivalences that you decide to use. So this is question number 3. So I'm going to choose the left hand side, which says that P and P implies Q, right? So what is that logically equivalent to? Now, I remember maybe from my rules of logic, okay, that I have a law that I have a law that says that P implies Q is equivalent to not P or Q. This is called the implication law. Right? So maybe I could use the implication law here. So this will become P and not P or Q. And then I could probably write by the implication law. Then what can I simplify again here? Well, I notice that I have an AND operator here. So maybe I can distribute the AND over the OR, right, throughout. So P and not P will go OR P and Q. This is by the distributive law. So just for space, I'm going to come here on my left hand side. So I'm going to write P and not P or P and Q by the distributive law. Now, what else can I do here? Well, I notice here that in my first parenthesis, I have P and not P. P and P are the same, and I have a negation here. And this is the complement law here. The complement law says P and not P is equal to some letter that is used differently. I'm going to use F. So I have F for P and Q. Okay, use the complement law. Complement law. And then to go from maybe here, I could absorb this inside here. No, I shouldn't say absorb because there is actually an absorption law. I can say that I can use the identity law, right, with F here, and the identity law will allow me to get rid of this F. So now this will be equivalent to P and Q only by the identity law, which is precisely the right hand side. So yes, this is fine. This is valid. Okay, so part A is valid. So let's move on to part B now. So once again, I'm going to take the right hand side and try to get the left hand side. Okay, so let's see how best we could do this. So part B says I have not P or Q or P and Q or R. Okay, so this one is a little bit long. Let's see how best we can do this. The first thing I notice here is that maybe I can take the negation sign and I can bring it on the inside here by De Morgan's law. Okay, so I'm going to bring, let's put my equivalent sign. So I'll have not P and not Q or P and Q or R. Okay, so I make it by De Morgan's law. So I'll just put DML because I don't have space. What else can I do here now? Well, I'm looking at this OR sign here. I can't really do anything with this yet. So I'm going to take the OR sign. I'm going to distribute it over P. And P is going to distribute as well over the Q. So I'll have P and Q and then P and R. Then I'll both have OR signs so I could combine them here. So let's do that all maybe, okay, let's do that in separate steps. So the first one will be, I'll have my first P and not Q. Let's leave this here for now. Then do the distribution of the AND sign first. I'll have P and Q or P and R. So I'll have by the distributive law. Okay, and then I'm going to bring the or sign on the inside. That is the associative law. So I'll bring it all under one umbrella. So one set of parentheses. P and Q, or P and Q, or P and R. This is by the associative law. Okay, so this is fine so far. What else can I do here now? So they all have or signs here, but I'm not seeing really anything I can do to get this right hand side here. I'm looking at the right hand side, and the right hand side here reads P and R or not Q. But how can I have P and R and then not Q? I mean, I could maybe use another law here, and I could switch these around and these around here to try and get the P and R in front. So maybe that might be able to work. Let's see. So I'm going to say that this is equivalent to not Q and not P, or Q and P. And since the right hand side has P and R, I'm going to leave this as P and R. This is by the commutative law. Okay, so what can I do now? I'm not seeing at this point here, unless I did something wrong previously, I'm not seeing anything else here that I could logically combine, right? Maybe resolution or something like that, but it doesn't seem to work out. So at this point here, I don't see any other laws I can use, so I'm going to say that this argument here is not valid, right? So this is an invalid, right? This is invalid. Not seeing any other laws that I can use here. Maybe the resolution might work, but it doesn't seem to break down any more than this. Okay, one could verify this by actually doing a truth table and see if the left hand side will be equivalent to the right hand side, and it does not look like, and I'm pretty sure that it doesn't look like it will be equivalent at all. Okay, so this argument is invalid. So this is the end of question 3. So let's move on to question number 4 now, where it says we have to use truth tables to determine whether the argument forms are valid, and then indicate clearly which columns represent the premises, etc., and give a brief explanation as well to show that we understand precisely what it means for a form of argument to be either valid or invalid. Okay, so I'm going to have to draw some truth tables. So let me get some space. Okay, so this is question number 4. So I have P implies Q, Q implies R, and therefore P implies R. Okay, and I have P, Q, and R. These are all the possible variables. Let me just confirm. Okay, yeah. And then for the premises, I have P implies R. Then I have Q implies R. And then for the conclusion, I have P implies R. Okay. So let me just... So let me now fill my truth table. A little bit more space here. So I'll have T, 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 F, 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 F. Then I'll have T, T, F, F. Okay, T implies R. So T and T will give me T. Let me take my time and do this so I don't make an error. T and T will also give me T. T and F. T. Nope. Sorry. It's T and F. That's F. Then I have F. 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 Oop, this is T here. F and T. And F. Then I have Q implies R. So T and T is T and F, then T, then T, then T, then F, then T, then T. And then finally the conclusion, okay, which is P implies R. So P implies R. Now T and T, we have T, then we have F, then we have T, then we have F again, then we have T, we have T, then we have T, T. Okay, now I need to check and see, are all my true premises giving a true conclusion? Let's check. T and T, T, this is fine. This is fine as well. Where else do I have? This is fine, this is fine. Okay, so all the premises give a true conclusion when it is true. So yes, this is valid. Okay. Oh, they said they wanted a brief explanation. So we have to say the argument is valid because in every row where both premises are true, this is 1, 1, 2, 3, 4, 5, 7, and 8. So we have 1, 5, 7, and 8. The conclusion is true. Conclusion is also true. Let's add also. Right? There are no rows where the premises are true and the conclusion is false. Of course, you can add that here as extra if you wish. All right? I think it's a good idea to add that there. So let's move on now to part B. So I have for part B, let me split the screen once again. Okay. So I have P implies R, Q implies, sorry, Q or V, sorry, Q or R, apologies. And then I have therefore P implies R. So once again, let's get all my variables down. I have P, Q, and R. For the premises, I have P implies R, I have Q or R. Then for the conclusion, I have P implies R. Okay. Okay, so let's go ahead and start now. P implies R. We have T, F, T, 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 T. Q or R, T and T, 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 F, T, 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 F, and F, or F, F. Right now, we're going to do the same thing again. We're going to fill out this and see where it's all true. So T and T, P implies R. Sorry. P implies R. T implies T. That's T. Then we have T and F. That's F. Then we have T and F. Sorry, T and T, T, F. Then we have, wait a minute, I don't even need to do this, right? If we could look here, we are seeing that this is fine. But look, we have true premises and a false conclusion. This is wrong. I don't even need to fill out the rest of the column because we have true premises, false conclusion here. So this argument is invalid. Okay, so this is good. So the argument is invalid. Because there exists a case where the premises are true, but the conclusion is false. Right? The conclusion is false. So no, it is not valid. So this brings us to the end of question 4. So let's move on now to question number 5. So we have quite a number of arguments here. We have to determine, they said that some are valid, whereas some exhibit errors, such as the converse error or the inverse error, etc. So there may be more. Use symbols to write the logical form of each argument. And if it is valid, what is the rule? If it's an error, state what type of error it is. Okay, so let's do the first one. So we have to take each one and break them up and then see if we have what type of error or validity, as the case may be. So this is question number 5. It says if a number is divisible by 4, then it is even. So I'm going to let P be equal to the number. The number is divisible by 4. I'm going to let Q be the number is even. The number is even. So if I use this where if a number is divisible by 4, then it is even. If a number is divisible by 4, then it is even. Then the number is not even, so not Q. Then my conclusion would be therefore the number is not divisible by 4, so not P. So this looks to me like modus tollens. So this is valid. You must say it's valid, and it's valid by modus tollens. Okay, this is the rule of inference here. So let me split the screen once again to save time and do part B. Part B says Maria studies biology and Kevin studies chemistry. Maria studies, and then it says Maria studies biology. And then that's it. Okay, let's write this out first. Unless this question has an error in it. Let P be equal to Maria studies biology. And Q be equal to Kevin studies chemistry. It's only 2 things it have. Okay, so let's see. It says Maria studies biology, that's P, and Kevin studies chemistry, Q, and then it has Maria studies biology, which will just be P. Oh, this is not this is valid. This is valid. This is simplification. Yeah, I thought it looked quite weird. Simplification. This is valid by simplification. So this is a little bit of a trick question here. You're probably looking for a conclusion with something with Kevin, maybe. Okay, but it doesn't have one. So this is valid by simplification. So let's look at part C now. It says if the alarm is set, so I'm going to let P be equal to the alarm is set and Q be equal to the building is secure. Building is secure. So I have, if the alarm is set, then the building is secure. So if the alarm is set, then the building is secure. And I have the building is secure. And I have therefore the alarm is set. This is the converse error. This is invalid. And this is the converse error. Okay. So this is question 5. So let's move on to question number 6 now. We have these very long set of premises here and a conclusion at the end. Okay, so these are a little bit tricky sometimes. Sometimes you don't even need all of the premises at all to derive the conclusion. So it says, deduce the conclusion from the premises and give a reason for each step by stating which valid argument form you will have used. So, okay, let me just split the screen once again because I'm going to forget all of these. I'll leave that. So I have A is not R implies P and not Q. Let me look at my conclusion. My conclusion is not T. So I'm not seeing that I actually have to use A yet. Maybe I'm seeing that I have T, sorry, not T, in none of from A to E. I don't have any at all. Nothing there has T except for B. And I want to get not T. To get not T, I'll have to use something like the modest ponens or tollens, right? But before I do that, I would have to get something to use the modest ponens or modest tollens with. So maybe I can use, I'm seeing I could probably use U with C. So I have to get another U to use with premise C, and then use premise C with, which is U implies not R, with B somehow to get back not T. So if we work backwards, I would have to look for, so I want not T. I'm seeing that I have something with T in B. But when I look at B, I'm seeing T and R. So I have to look now and see where do I have R again. I have R in C, which is U implies not R. Now I'm looking to see where I could use U now. I'm seeing I have U in E. So we're working backwards, right? I have U in E and I want U only. So how to get U only? Well, I have to use E for sure. And I can use D with E to get U by itself, then somehow use U with C, and then somehow use C with maybe something with B to take out that R completely so I could just get T by itself. Right? So we identify where the conclusion is inside the premises, and then we keep working backwards to see where we can use another premise to start with. Right? So that's how I identified that I can start with something with E. Right? So my first question, I'm going to use not W. This is from D. I'm going to use U or W. This is from, and by elimination, I'll just get therefore by elimination. Now I said I wanted U because I want to use it with C, right? So now I'm going to call this, let me call it something like 1 to keep track of it. Then I'm going to use U implies not R. It's from C. And then I'm going to use back U, which is from 1. And I'm going to use mode exponens. I'll just put MP for here, right? Mode exponens. And I'm going to get not R. Let's call it something 2. Now I said I wanted not R by itself, so I can use it with B. So if I look at B now, B says I have T implies R. This is from B. And then I have not R, which is from 2. And then if I use mode exponens, I'll just put MT for now. I'll get not T, which is exactly the conclusion. Right? So that is how we were trying to think about something like this. So this is part A. Now part 1. Subpart 2 has quite a lot more. And somehow I have to get U and W. So in order to do larger ones like these, where we have quite a lot of premises and one conclusion, it's a good idea to break up these into different cases, right? Similar to what I did before, but with more subcases. And usually when you break them up into subcases, then you can put them back together and you can get the conclusion. So the first thing is that I have to get something with U and W, but a conjunction. I'm seeing I have W in G, so I'm going to have to use that at some point in time. And I have U in F and F only. So if I want to use G at some point, then that means I'd have to get rid of that T. And that T there is in C. So that should probably be my starting point, right? Because I have not T in C. So let me write this out. Subpart 2. So I said that I have identified my starting point. So my starting point has to do something with C, but I just need T. That's, well, if I look at E, I'm seeing that I have not S. So I could use mode exponens with not S. This is from E. And then I have not S implies not T. This is from C. Then I could use mode exponens. Then I have to put therefore not T. Let's call this number 1. And I said I wanted to use this because I want to use it with W or T from G. So I'm going to write W or T from G with my not T. This is from 1. And then if I use elimination, I'll get W. This is by elimination, right? So this, I'm going to call this number 2. So I have the W part of my conclusion. What about the U part? Now, I'm going to pause here and I'm going to really think about it. I don't want to use back this W in another premise and then lose it, right? So let's keep it here for now because I'm seeing that in H, I have W. So because I have it, I could use some rule maybe and I could bring it together with the U, but I need the U. The U now is an F. But the F has P and not P and R. And I need to get rid of that not P and R. What has P and R again? Well, A has P and B has R. So we can reuse premises even though we used it before, right? So what I'm going to do is I'm going to I need P and R, but A has P and I need P. So if I need P and P is in A and I have P implies Q, then I have to look and see where I have Q now. I have Q in D, which is not Q. So I need that not Q. How to get that not Q? I can reuse premise E with not S. So I'm going to pause. So this is like one set of work in here. I'm going to pause here. I'm going to go not S from E. I'm going to use not Q or S from D by elimination again. Elimination is quite convenient. And I'm going to get not Q. Perfect. Because I wanted to use this with my A. Because remember, I wanted that not P part. So I'm going to, so I have P. P implies Q. This is from A. I have not Q here. This is from 3. This will give me not P. Let's call this number 4. Number 4. Oh, this is by modus tollens, right? Okay. What else now? Now I have not P. I wanted the not P because I wanted to get something to use back with F. So in F, I have the not P part. The only part I need now is the R part. How to get the R part. Remember my goal here now, remember these are division into cases. In this sub case, I'm trying to get the U out of F. But the problem is that I have a not P and R. So I'm looking for where I can get not P and R, right? I already identified I have not P here. Now it's time to get the R part. And I'm seeing that I could use back not S again with B because B has R in it and I could just get R by elimination again. Okay, so I have not S. This is from E again. And I have R or S. This is from B. And this will just give me therefore R. Elimination again. This is, what am I at? Number 5. Okay, now I have R. So I'm going to take R and my not P, I'm going to put them together. So not P, which is number 4, and R, which is number 5. I'm going to put them together. So to get not P and R, or by conjunction, huh? By conjunction. This is number 4, 5. This is number 6. Okay, now I have not P and R, which means I could go back to F now and I can extract my U from there. Okay, so now I have not P and R implies U. This is from F. And finally, I have the not P and R. This is from 6, right? And I could use my modus ponens and I'll get therefore U. This is number 7. Perfect. Now I could use U and I have to go all the way back up to number 2 where I got W by elimination and I could put them together. So I'll take U. This is from 7. And I'll take W, which is all the way from 2, and I could bring them together and I'll get U and W by conjunction. And this is what I wanted. Okay, I hope that we could have followed that along. So this is the end of question 6. And finally, we make it to the last question. Okay, which is again, has a bunch of instructions. Let's read it here. It says to write each of them in the predicate / quantifier form. And then, of course, determine whether it's valid or invalid, right? And state what rules we have. So the first one, let me just split this screen again. All right, perfect. This up here, this is the last question. So It says all real numbers greater than 5 are positive. Let A be a particular real number such that A is strictly greater than 5. And then our conclusion is therefore A is positive. Now, I'm talking about real numbers here on the whole. So I have identified firstly my domain. So you would say let the domain be set of real numbers. The first statement, the first sentence here says all real numbers greater than 5 are positive. So I'm talking about things that are greater than 5. So let g of x be x is strictly greater than 5. And then talks about in the second sentence, let a be a particular real number such that a is greater than 5 again. And therefore a is positive. So we are talking about the positivity of the number. So I'm going to identify that again. X is positive. Positive. Right? It's X, right? Not A. Because when we start to speak about which real number, then we could put in A. Right? So not A, right? X. Right? This is my domain here. So we have to write this now in our predicate quantifier form. So my first premise, let's call it P1. It says all real numbers greater than 5 are positive. So I write for all x, that is real, g of x implies p of x. Right? X is greater than 5 implies p of x. And the second one says let a be a particular real number such that a is greater than 5. A is greater than 5 will be g of a. Right? This is why I put g of x is equal to x strictly greater than 5 and not g of a. Right? Because now we're starting to talk about the particular real number a. And then of course the conclusion would just be, what is it? Therefore a is positive, then just write p of a. Therefore. Right? So this is of course valid. Right? This is valid. This is our universal modus ponens. Universal modus ponens. Okay, so this is part A. Part B, sorry, subpart 2 says that all employees, all who attended the workshop received a certificate. Maria received a certificate, therefore Maria attended the workshop. Okay, let's see how to write this. First thing, let's identify the domain. The domain, it is not the certificates, it is the employees, right? So let the domain be all employees. Now let's break it up just like we did before. It says all employees who attended the workshop received a certificate. So Maria received a certificate, therefore she attended the workshop. So the employees are going to the workshop, right? So we have to talk about the attendance of the workshop. So I would just use a of x for a particular employee. Let's use x attended the workshop. Okay. No, it says x. Sorry, not x. Maria received a certificate, therefore she attended the workshop. So if you have attended that workshop, then you would have received a certificate. So I'm going to use c of x for certificate. I'll put x received a certificate. Okay. And because we are talking about Maria here, right? If you want, you can add this as well, right? We're talking about Maria specifically. You can put I'll put small m, Maria, because I know at some point I'm going to speak about her. Okay, so let's write this now. So 1 all employees, so I already know I have the right for all, X, who attended the workshop received a certificate. Okay, all of them who attended, they received a certificate. So C of X. Premise 2. Maria received a certificate. So C for certificate. And we are speaking about Maria, right? Not X, not all of them, just Maria. So I put small m. So C of M. And then the conclusion is, finally now, therefore Maria attended the workshop. Now, be careful here. Maria attended the workshop. Now, remember that C is for the certificate, A is for the attendance. So I'll have to put A, that the attendance was there, but for who? Maria. So A of M. Okay? So A of M. So now, is this valid or invalid? Of course, this looks exactly like the converse error. Right? This takes the form of the converse error. So this is invalid. This is invalid. Okay? Because if you think about it logically, it says that Maria received a certificate in sentence 2. We don't know what she received the certificate for. Maria could have received that certificate for another reason. It doesn't have to be for this attendance. So therefore, let me get a different color. So therefore, this C of M here doesn't follow logically from the A of X. Sorry, C of X. It doesn't follow from this. So C of M, if I said A for M from Maria, implies C of M from Maria. Is this workshop what she went to? Does this imply that she received a certificate for this one? How do I know that? There is no way to know that, so it doesn't logically imply that. Right? So this is invalid. This is the converse error. Okay, and this brings us to the end of assignment number 1 solutions.